Hello everyone. Now I'll continue with the session 6 of module 5, continuation of strain measurements. This session belongs to certain theory of strain gauges and as well relationship between a gauge factor and Poisson's ratio. So first, the change in the value of the resistance by straining the gauge may be partly by an elastic behavior of the material, and moreover, if an elastic material is subjected to a tensile force, its longitudinal dimension will be increased while the lateral dimension decrease. You are well known longitudinal dimension in the sense length, linear dimension in the sense diameter, and resistance of a conductor is given by an equation R is equal to rho into L by A. We are well known now all the parameters. Rho is resistivity of the conductor, L is equal to length of the conductor, A is equal to cross sectional area of the conductor. So if an resistance of a strain gauge increases because the resistance of a conductor is directly proportional to its length and inversely proportional to its cross sectional area. See, if we need to design a strain gauge properly, we should have to know the concept of piezoresistive effect, which means that an extra change in the value of resistance is attributed to the change in the value of resistivity of a conductor when strained. This term we call it as piezoresistive effect. See, now the relationship between a gauge factor and Poisson's ratio we'll discuss. Let us consider a circular wire of resistance. This is a sketch which shows a circular wire of resistance of diameter D and cross sectional area A and length of the conductor L and subjected to a tensile force. Now, according to the equation 1, that is R is equal to rho into L by A, we are well known L is length of the wire, A is the cross sectional area, rho is resistivity of the material. So if this wire is subjected to a tensile force, there will be a tensile stress which is induced, that is represented by S, which causes a positive strain. Then length increases and the cross sectional area decreases, that is longitudinal dimension increases, lateral dimension decreases. Correspondingly, delta L, delta A, delta D are the change in the length, cross sectional area and the diameter respectively. Capital R is the resistance of the strain gauge wire before straining. Then delta R is equal to change in the resistance of the strain gauge wire after straining. So in order to determine how the change in resistance depends upon the physical quantities of the material, that equation 1, this equation 1, we need to differentiate with respect to tensile stress S. Now when I differentiate with respect to S, that is dr by ds is equal to rho by A into dou L by dou S minus rho L by A square into dou A by dou S plus L by A dou rho by dou S. That is we will call it as this as equation 2. See, these are partially differentiated. Now we will divide this equation 2 throughout by R. Now dr by ds into 1 by R is equal to 1 by L dou L by dou S minus 1 by A dou A by dou S plus 1 by rho dou rho by dou S. I will call this as equation 3. Now this equation 3 is very much evident that per unit change in resistance is due to two different factors, that is unit change in length and as well as unit change in cross sectional area. Say first per unit change in the length is delta L by L, and unit change in cross sectional area is delta A by A. Now we are well known the wire is in cross sectional area A is equal to pi by 4 d square, where d is the diameter of the wire. Then differentiate, right, with this whatever the area with respect to S once again. Then dou A by dou S is equal to 2 into pi by 4 d dou d by dou S. And finally, when you simplify this equation to extract 1 by A, dou A by dou S is equal to 2 pi by 4 into d. See, when I taken this factor to numerator, pi by 4 d square, delta d by dou d by dou S is equal to 2 by d dou d by dou S. Rearranging the terms. Thus equation 3 becomes this equation 3 becomes dr by ds into 1 by r is equal to 1 by L dou L by dou S minus 2 by d dou d by dou S plus 1 by rho dou rho by dou S. We are well known Poisson's ratio is equal to lateral strain by longitudinal strain. Lateral dimension is the diameter, then lateral strain is dou d by d, and longitudinal dimension is length, then longitudinal strain is dou L by L. Now when I simplify and interchange this thing, cross multiplying, dou d by d is equal to mu into dou L by L. Now see, the equation gets alters, right? When I substitute back this whatever the term into this equation, now we will get it 1 by r dr by ds is equal to 1 by L dou L by dou S plus mu 2 by L dou L by dou S plus 1 by rho dou rho by dou S. See, there is small change in the variations, right? And this particular equation 4 can be written in a simple manner. Delta r by r is equal to delta L by L plus 2 mu delta L by L plus delta rho by rho. Now we are well known gauge factor is defined as change in resistance by change in length, that is delta r by r divided by delta L by L. Then delta r by r is equal to gauge factor into delta L by L. When rearranging the terms, we are well known this term delta L by L, change in length by original length, is strain epsilon. We will re-alter the term now. See, we will get it 1 plus 2 mu into dou rho by rho divided by dou L by L. Then again I will say this is epsilon. Now this entire term is very negligible, right? And still further we can simplify it, which the value that is rho, you are well known resistivity of the material, it gets strained, we need to neglect it certain times. The gauge factor is equal to 1 plus 2 mu. I will call this as equation 5. Now this equation 5 is valid only when piezoresistive effect has been negligible. Further, the Poisson's ratio of many metals is in between 0 and 0.5. And now the gauge factor for metallic strain gauges cannot be more than 2. Basic Wheatstone resistance bridge and method of strain measurement. So this is a bridge, Wheatstone bridge, which is of composing R1, R2, R3 and R4 of 4 different resistance, which are highly sensitive for strain measurement. It has been connected by a junction BD, right? And the basic principle of this bridge may be applied in 2 different ways, by either null method or a deflection method. we'll discuss first deflection method. See this V-stone bridge which has been used has to be adjusted so that the bridge is balanced between B and D is equal to 0. See, in order for the bridge to balance, the ratio of resistance of any two adjacent arms must be equal to the ratio of resistance of remaining two arms. That is, R1 by R3 is equal to R2 by R4. See, that only have been written here on the form of equation. If the resistance R1 changes, it will unbalance the bridge. So the voltage will appear across B and D, causing a meter reading, that is RM. See, now the meter reading is an indication of the change in R1 and actually can be utilized to compute this change in RM, since the meter deflection indicates resistance change. This concept we call it as a deflection method. Now we look into a null method. See here in the bridge, V-stone bridge circuit, again R1, R2, R3 and R4 which have been connected with meter RM, right? Now one of the resistor is adjusted manually, any one of the resistor, generally we'll take it as R1 changes, causing a meter deflection R2, right? Now causing a meter deflection, and R2 can be adjusted manually until its effect cancelled, that R1 and bridge is returned to the balanced condition. See, the adjustment of R2 is guided by the meter reading. R2 is adjusted so that meter returns to null position or a zero position. See, in this case, R1 value is related directly to change in R2 required to affect the balance. So, this whatever the concept we say null method. See, now a V-stone bridge arrangement for the strain measurement by using certain specimen. See it, this sketch which shows a particular specimen strained it, and see here a tensile force which has been strained, and there will be two different arms, R1 and RM2, which have been connected, right, with a battery onto the junction here. See, it is most convenient method for use with the strain gauges, because it may be easily adjusted to null for zero strain, and also it provides a means for effectively reducing temperature effects. So in this arm 1 consists of a strain sensitive gauge mounted on the test item. See here you can look into this arm 1, right, which has been mounted, right, onto the test item, and arm 2, see here arm 2 formed by similar gauge mounted on a piece of unstrained material. Okay, see as that of the test item, and which is placed nearer the test location so that the temperature will be the same. See, if the arm 3 and 4 contains a fixed resistors, right, for good stability, and portion of the slide wire resistance, then D, this whatever the D which is required for balancing the bridge. If the deflection method of a strain measurement continuous reading from the change of strain to another without rebalancing, and moreover this is convenient but less accurate, as the bridge output tends to non-linearity if the strain is successively increased or decreased. Certain requirements for accurate strain measurement. First one, the gauge should be small in size and easy to mount on the component. Second one, the profile should be low as possible. so that it will respond in close agreement with the change in surface to which it is fixed. The gauge should be highly sensitive in deflection of the measured strain with a low sensitivity in a transverse plane, that is in the cross sensitivity say. And stiffness in all directions should not be such that the stiffness of the tested surface is modified. And calibration should be make it easy, should remain stable with the time or dynamic loading or sometimes change of temperature, pressure or humidity. Next, the speed of response should be high such that time log is negligible. This is very very important consideration we need to observe. And evaluation of complex strain patterns should be obtained from as small a number of strain measurements as possible. Gauges should be inexpensive, reliable and readily available and available in variety of types and sizes to suit a wide range of applications. Immersion in liquids should not modify performance. See, immersion in liquids, see, should not modify the performance. Performance characteristics are different. So now we look into temperature compensation of strain gauges. Resistance type strain gauges are sensitive to temperature changes. If there is any change in variation in temperature which influences the strain gauge readings. See some of the observations which they were made it during temperature influence. First one, the gauge factor of the strain gauge is affected by temperature owing to creep. Second one, the resistance of the strain gauge element varies with change in temperature. Third one, the strain may be induced in the gauge due to differential expansion, which is between the test item or the member and the strain gauge bonding material, right? And these temperature effects may be compensated in two different ways. The first one is adjacent arm compensating gauge and self temperature compensation. When any one of this method we can compensate temperature. First one we look into an adjacent arm compensating gauge of strain gauges. See this condition uses the arms which have been balanced. You are well known with a resistance adjacent arms of resistance R1 by R2 is equal to R3 by R4. If the arm 1 and 2 are alike, right, you are well known, and mounted on similar materials, if both the gauges should experience a small resistance shift of delta RT caused by temperature change, then this whatever the equation we can modify it R1 plus delta RT divided by R2 plus delta RT is equal to R3 by R4. Just for this equation we need to add up both numerator and denominator by delta RT. Okay, this is the test gauge, right? And we are compensating this particular gauge. Okay, this is the R1 and this is the R2 and this is R3 and this is R4 with a galvanized meter. See here with respect to this we can change output is unaffected by the change in temperature, whereas in case of self temperature compensation, so a gauge should exhibit zero change of resistance with change of temperature when bonded to a specified material. To know self temperature compensation, we need to consider a conventional advanced gauge bonded to a steel base, and the coefficient of linear expansion of the material which has been used generally in alloy is about 15 micro meter degree centigrade per meter, while the coefficient of steel the value which will be around 12, and thus under rising the temperature of free expansion of the gauge which can be prevented. As a result, the gauge is in the compression state, and delta R by R or dr by R from the source is negative. That term is negative because compression we are generally identify decrease in dimension, no? So then it will be a negative. The thermal coefficient of resistance of the gauge itself is positive. Thus dr by R from the source is positive. See, if these resistance changes are equal and opposite, then the change of resistance due to temperature is zero from the source. See, for this, a similar gauge which is bonded to aluminum, a coefficient of 12 micrometer per degree centigrade per meter would be in tension. The most widely used self-compensated gauges made from specially prepared selected melt alloys for use on specified materials. During the melt, that is in the liquid state itself, they'll get select a particular melt alloy. See, the temperature coefficient of resistance of the gauge by suitable heat treatment has to be made it during manufacturing. For physical reasons such as matching can only be ensured over a limited range of temperatures. To overcome these limitations, the manufacturers calibrate selected gauges from each batch which has been produced. See, this is a diagram which shows strain versus temperature. See, the strain values and the temperature values correlated, and see, observe from this curve. See, the strain gets restricted only as the temperature increases, correct, no? See, in another way we can say the temperature is directly related to a strain. Say another type is made by connecting two different wires in series to form the grid, and one having a positive and the other is a negative gauge factor, and which increases in resistance in one wire due to temperature is almost equally compensated by similarly decreases in the other. That's why which is called it as self temperature compensation. Now we'll see how exactly the calibration has been performed for strain gauges. You are well known. Calibration refers to the just a procedure which is made to operate strain gauges accurately with a known input corresponding to output which has been measured. See, the procedure cannot be applied in bonded resistance strain gauges because of its nature, and moreover the calibration of strain gauges, the value of both the gauge factor and gauge resistance should be known accurately, otherwise it is impossible to calibrate. The gauge factor for each of the gauge is provided by the manufacturer within an indicated tolerance of about plus or minus 0.2% it is, and calibration consisting of determining the system response by introducing a known small resistance change at gauge and calculating the equivalent strain. See, you can observe here. See, the resistance change is induced by stunting a relatively high value precision resistance across the gauge. See, when the switch S, this is the switch S is closed, the resistance of the bridge R1 is changed by delta R. See, if Rg is the gauge resistance, Rg is what? Gauge resistance. Rs is the stunt resistance. This is the stunt resistance. This is the switch, right? Rg is the gauge resistance. The resistance of the arm 1 after the switch is closed this connection switch is closed, becomes Rg into Rs, Rg into Rs divided by Rg plus Rs. Say if the resistance of the arm 1 before the switch S is closed, I can say Rg. Then resistance of the arm 1 after the switch is closed, I can represent by this equation Rg into Rs divided by Rg plus Rs. Now change in resistance is delta R, that is equal to Rg into Rs divided by Rg plus Rs minus of Rg. Now when I simplify it, minus R square G divided by Rg plus Rs. Now the strain in the gauge epsilon is equal to 1 by gauge factor into this whatever the term delta Rg divided by Rg. See now by substituting delta R for delta Rg, the equivalent strain is found by epsilon E is equal to minus of 1 by gauge factor into Rg by Rg plus Rs. See a number of equivalent strain values which can be obtained by stunting the different stunt resistors across Rg. See this is very most important aspect in the strain gauges. Graph generally plotted by change in resistance delta R, which is equivalent in strain manner. Okay, the strain which is corresponding to the measured resistance changes when the gauge is bonded on the test member, which can be read from the plot of epsilon E versus delta R plot. That is strain, that is versus change in resistance plot. Now we'll discuss certain multiple choice questions for this session. First question: a strain gauge with high sensitivity and high gauge factor is, options are nichrome transducer, B semiconductor strain gauge transducer, C platinum tungsten alloy transducer, D none of the above. Then definitely it will be an high sensitivity with a gauge factor. High gauge factor is for what? Maybe an p-type semiconductor or n-type semiconductor. Values would be around 170. Then semiconductor strain gauge transducer it is. Then question number 2: rosette strain gauges are used for measurement of strain in. See here the option will be A horizontal direction only, B vertical direction only, C complex parts, D simple parts. See in the rosette strain gauges which can be used for 3 different directions. See X, Y and Z. Even in transverse direction also you can choose it. See here the complex parts we can measure the strains. Answer will be the complex parts. Question number 3: a strain gauge should have a high value of gauge factor. Options are to reduce hysteresis effect, to give a linear relation between applied strains and resistance change, C to increase sensitivity, D to reduce or eliminate the effect of variation in ambient temperature. The answer, see, read out the options carefully and see the strain gauge should have high gauge factor which is depends on to its increase in sensitivity. Then definitely answer will be to increase sensitivity. Fourth question: the ratio of resistances of any two adjacent arms must be equal to the ratio of resistance of the remaining two arms in measurement of strain in dash method. See here they have given null, deflection, 0, datum. See in deflection method Wheatstone bridge, that is R1 by R2 is equal to R3 by R4. Then definitely it will be a deflection. Fifth question: the bonding element in strain gauge must possess the bonding element in a strain gauge must possess. See, now the options were 0 insulation resistance, then B high insulation resistance, C low insulation resistance, D any of the above. See, now the options are A 0 insulation resistance, B high insulation resistance, C low insulation resistance, D any of the above. Now answer will be high insulation resistance. See, bonding material which has been used as an insulator, then definitely high insulation resistance it is. Question number 6. Gauge factor of thick film resistor is 1, 10, 100, 1000. See, among these options, C, that is the value of the thick film resistor will be in 3 digits. Within 3 digits it should be 100. Seventh question. To detect a very small change in resistance, strain gauges are configured with. Say options are A. Wheatstone bridge, B. Maxwell bridge, C. Hayes bridge, D. Anderson bridge. See here, with respect to the strain gauges, Wheatstone bridge which has been used. Correct, no? Question number 8. Which of the following is a practical application of strain gauges? A. Cables of civil bridges, B. Aerospace engineering, C. Railway engineering, all of this. See, all these whatever applications which have been given, one another way, either it may be a compressive force or a tensile force which has been exerted. Correspondingly, there will be a compressive strain or a tensile strain which exerts. If you want to know the deformation, then we need to use it as strain gauge. Then definitely all of the above is the answer. If L1 is the original length of a certain wire and L2 is the new length after an external force is applied, then the strain is mathematically written as epsilon is equal to L2 plus L1 by L1. Epsilon is equal to L2 minus L1 divided by L2. See, epsilon is equal to L2 minus L1 divided by L1. Epsilon is equal to L2 minus L1 divided by L2. The answer you are well known, delta L by L it is. Final length minus initial length divided by initial length, it is L2 minus L1 divided by L1. Answer is C. Okay. Finally, the 10th question. Which parameter of a strain gauge varies with the applied force? The dash of the strain gauge varies with the applied force. See, A is resistance, B is capacitance, C is inductance, D is flux. See, moreover, for the resistance strain gauges, generally resistance of the strain gauge varies with applied force. Correct, no? A is the answer.